Watch a freight locomotive pull out of a station and your eyes go straight to the obvious places. The horn, the headlights, the pantograph sparking on the wire, the huge driving wheels grinding against the rails. But scan a little lower, somewhere between the bogies, and you'll spot something that doesn't quite belong on a modern machine. A small steel container with a thin pipe pointing straight down at the wheel. It's plain, almost crude, and it's on every locomotive in the world, from a century-old steam engine to a brand-new electric freight hauler rolling off the line this year. Inside that little box is something stranger still. Sand. Literal sand. Why does a 200-ton steel machine, capable of dragging 4,000 tons of cargo, need a bucket of beach to do its job? Once you understand what that sand is actually fixing, you will not look at a train wheel the same way again. The first guess almost everyone makes is wrong. People assume it's a braking aid, like the gritty mix highway crews spread on icy roads. That's not quite right. Trains do use it under braking, but that's the secondary job. The main reason that Sandbox is there, the reason it has survived nearly 2 centuries of engineering progress, is the opposite. It's for starting, for pulling away from a stop, for climbing a grade with a heavy load, for getting massive metal wheels to bite hard enough on metal rails to actually move the train forward instead of just spinning helplessly in place. And before you write it off as a quaint holdover from the steam age, know this. It's standard, sometimes legally required, on the newest locomotives running today. The modern versions are computer-controlled. To understand why a multi-million-dollar engine still relies on something this primitive, you have to look at where a train actually touches the world. Here's the strange truth. A train is the heaviest moving thing most of us ever stand near, and it balances on almost nothing. Each steel wheel rests on the rail through a contact patch roughly the size of a small coin, around 1 square centimeter. That's it. The full weight of the locomotive, plus every wagon behind it, plus every ton of cargo, presses down through a chain of tiny elliptical patches no bigger than a fingertip. Inside each one, pressures climb above 1,000 megapascals, far higher than under a car tire. This isn't a flaw, it's exactly why trains work. Steel on steel has astonishingly little friction. A train wheel glides roughly 1,000 times more freely than a rubber tire on asphalt. That low friction is the railway's superpower. It's why a single locomotive can haul a load that would need 100 trucks. But the same property is also its weakness. The slick interface that makes trains efficient also means the wheels can spin freely under power or skate uselessly under brakes, the moment anything interferes with the grip. The thing that makes trains amazing is the thing that makes them fragile. So why not just fix that? Why not bolt on something grippier? The answer is that every intuitive solution destroys the railway. Rubber tires would wipe out the efficiency that makes rail uniquely good at moving freight. Roughening the rails would wear them out in months and demolish the wheels along with them. Adding more weight over the driving axles helps a little, but only until the bridges, the axles, and the track itself start to break. What engineers actually need is something much more surgical. A way to spike the friction temporarily, locally, in the exact place where the wheel meets the rail, only when you need it, and only there. Without altering the wheel. Without altering the rail. Without paying for it the rest of the time. Once you frame the problem that way, the answer almost has to be what we have. The mechanism is beautifully direct. A small, precisely aimed pipe drops fine, dry, angular silica sand into the gap right in front of the driving wheel, milliseconds before the wheel rolls over it. The wheel crushes those grains into the contact patch. The hard, sharp particles briefly embed in both surfaces, creating a microscopic interlock. On a wet rail, where friction can fall to 15%, sanding pushes it back up to 30% or more. On rails coated in autumn leaf mulch, where adhesion can collapse to barely 1.5%, sand is sometimes the only thing between the train and a slide. It isn't really pouring sand on the rails. It's injecting an abrasive into a microscopic combat zone the size of a coin, exactly where the physics is failing. Think of a violinist drawing rosin across a bow. A temporary roughening, not a permanent change. And one tiny detail decides whether the whole thing works. The sand has to be bone dry. Wet sand cakes clogs the pipe, and the locomotive is suddenly running blind into a slick rail, which is exactly why old steam locomotives kept their sand in a dome perched on top of the boiler. Those iconic mushroom-shaped bumps weren't water tanks. They were sand-drying chambers using engine heat to keep the contents pourable. The idea is older than you'd guess. In 1841, a New York stovemaker named Jordan Mott patented the first proper locomotive sander, a small funnel-shaped box that trickled sand onto slipping wheels. Before that, train crews literally shoveled sand by hand from open buckets while the engine crawled up a grade. Mott's box was crude, but it set the template. American railroads put the sandbox high on the boiler because the heat kept it dry. British railways, hemmed in by tighter tunnels and bridges, mounted it lower, on the sides. Then in 1886, a Midland railway engineer named Francis Holt added a transformative twist. He used boiler steam to blow the sand through the pipes instead of letting gravity drag it down. That solved the clogging problem and stopped the wind from scattering the grains before they reached the rail. It worked so well that locomotives previously dismissed as too slip-prone, like the elegant single-driver spinners of 1887, suddenly became fast and reliable. The small box hiding under that brand-new electric locomotive is the same idea, refined for almost 2 centuries. And here's the twist nobody expects. More sand isn't always better. The same grit that saves trains can also blind them. Modern signaling systems detect where a train is by passing a low electrical current through the rails. When the steel wheels roll over, they short the circuit and the system knows. But a layer of crushed dry sand on top of the rail can electrically insulate the wheels from the steel below. On the 1st of August, 2013, 2 S-Bahn trains nearly collided at Mainz Hauptbahnhof in Germany. Investigators traced the cause back to too much brake sand on the tracks, which had cut the train detection signal. Swiss Federal Railways now forbid sand-assisted braking on certain locomotives. German rules restrict sanding at low speeds. Sand can also wedge into switch points and accelerate wheel wear. That is why modern sanders are no longer dumb gravity feeders. They're compressed air, computer-controlled, slip sensor-triggered systems that fire tiny, precisely metered bursts only when the wheels are actually starting to lose grip. The simplest-looking part of the train is quietly one of the most surgical. So watch that locomotive pull out of the station again, and find the little box. Find the thin pipe. Every time a freight climbs a wet autumn grade through a film of crushed leaves, every time a commuter train brakes cleanly on a frosty rail, every time the wheels grip when the world tells them they shouldn't, a controlled pinch of sand is hitting a patch of steel the size of a coin. The sandbox is older than the light bulb. Nothing has ever replaced it because nothing else fits the problem this cleanly. And once you know it's there, you cannot unsee it.